This conference will now be recorded.
Good evening, students. We have been discussing PYQ mains, JEE mains from JEE mains, and we had already discussed JEE mains paper 6th September, the first shift. So today onwards, we'll discuss the questions from the second shift, shift 2. So we have got today's first question. When a car is at rest, its driver sees raindrops falling on it vertically. That means rain initially is dropping vertically when the car so you can take this as car anyway. So when it is at rest, raindrop is vertically downward. It is falling vertically downward. Let us say the speed of that is something some v rain say, and this is since it is at rest, so it is at rest. This velocity v rain is with respect to ground. Okay, v rain with respect to ground. When driving the car with speed v, now the car has been driven by the driver with speed v say. Okay, then the driver says that the raindrops are coming at 60-degree angle from horizontal. 60-degree angle from horizontal. Okay, so let us say it is moving in this way. So raindrops are actually coming. If I say that, see, rain is coming like this, okay. So when it is moving with v, okay, so therefore it will have actually two components like this, okay. So with the horizontal it is 60-degree. All right, so I can actually write down this tan theta is equal to, or let us write that the v rain, okay, v rain with respect to ground. See, v rain with respect to car, v rain with respect to car is v rain with respect to ground minus v rain with, sorry, v car with respect to ground. Okay, this is what it is. Now let me write down this v rain with respect to ground. I have taken, let's say this is u, so I have taken u, and that is along minus j cap direction. Okay, and this is the vector, this is actually along y, along x cap direction, so v x cap. Okay, v x cap. All right, so in this case, if I want to write this angle tan 60°, this will be this this is in the y direction, so this is minus u by minus v. Okay, minus u by minus v. Okay, so now the question is, what is tan theta? Tan 60° is √3, so u is equal to √3 into v. So this is what I get from here. Now the condition is that when the driver further increases the speed of the car to this 1 plus beta v, this angle changes to 45. This angle, the angle that the rain makes with the horizontal, becomes 45°. So similar way, if I draw this, okay, so this will be somewhat like this. This is with horizontal like this. This is 45°, and this is the vertical one. So anyway, my velocity is somewhere like this. Okay, this is v. So here also I can write the relative velocity of the rain with respect to ground is relative velocity of the rain with respect to, I'm sorry, this is rain with respect to car, I have to write. So rain with respect to ground minus velocity of car with respect to ground. So we know this one is this one we have taken as u, and it is actually minus j cap direction, and this is along positive x direction. Okay, now let us see, this is tan of 45° is equal to this vertical component, so minus u divided by minus of 1 plus beta into v again. So this u is actually, okay, I'll just calculate the u. Okay, so here it is, see, 1 over √2. That means, you know, u will be actually 1 plus beta into v by √2. So if we compare this equation, so suppose this is equation number 1, this is equation number 1, and this is equation number 2. So they both are actually same, so I can just write 1 plus beta v by √2, that is equal to √3 v, √3 v. Now v goes up from both sides, so this will be beta is equal to 1 minus, sorry, √6 minus 1, √6 minus 1. Okay, so we need to find out what is the value of beta. Okay, so beta is this √6 minus 1. Actually you can do one thing, see, just short way to do that, √2 into √3 minus 1. So root over 2 is actually it will be nearly this multiplication will be nearly 2.4. Okay, if I take the first decimal or second decimal after second decimal, this approximately. So this is coming around 0.4. Okay, so 0.44 kind of that. So let us see the options. See there are options nearly this 0.41, 0.5, 0.37. Anyway, I should get 0.37, but I'm getting nearly 0.44. Just let me see where we have done a small mistake. So I'm sorry, this is where we have done the mistake. See, 10:45 degrees 1. Okay, 10:45 degrees 1. So that's where we had this problem. Okay, anyway, so we'll get it exactly 0.37. So this is u is equal to this much. So from the previous value we had got u is equal to root 3 v, and this is 1 plus beta into v. So v goes up, so root 3 minus 1, root 3, you know, this 1.375, something like this, minus 1, so this will be nearly 0.37. Okay, all right, so this is where, okay, so 0.37 will be the answer for this question. Okay, let us go to the next problem. Okay, so this problem says a particle is moving in xy plane, experiences a velocity dependent force, and this is given here, where vx vy are the x and y component of the velocity. A is the acceleration of the particle. Then which of the following statements is true for the particle? Okay, so what is given here? Force is given, vy I cap plus vx j cap. Okay, so if I want to get the acceleration, I just do this. Okay, then I get the acceleration. So vy by m I cap plus vx by m j cap. Okay, this is the acceleration. Okay, now the question is, see, if we want to write down what is the acceleration, see, this can be written as I cap dvx dt, right, plus j cap dvy dt. So can I write from here that dvx dt is equal to vy by m. Similarly, I can write dvy dt is equal to Vx by m. Okay, now from here, if I do one thing, if I just take the ratio, look, I have got, okay, I what I'll do, I'll do this dvx dt ratio, I'll take dvy by dt. Okay, this is what I'm trying to do now. So what I'm trying to do here, I'm just trying to do this dvy by dt, say, divided by dvx by dt. Okay, so look here what we get from here. I'll get, see, dvy by dt means vx by vm. Here it is vx by m, and in for this we'll get vy by m, and say this is dvy by dt, and this dt will actually cancel each other, and finally what we will get, dvy by dvx is equal to vx by vy. Okay, so from here, look what we can do, we can just integrate vy with dvy and vx with dvx, and let us take integration constant to be c. So from here we'll get vy square by 2 minus bx square by 2 is equal to c, or vice versa. Okay, we can do another way also, we can just do the reverse way also, then the constant I will just change, vx square minus vy square is equal to minus 2c, which I am taking as another constant key. Okay, all right, now I have got a relation between vx and vy. All right, so with this, see, the kinetic energy of a particle is constant in time, that is, that part is not happening. Okay, kinetic energy in this case, when the force is not a constant or not a conservative one, not a constant one, then the kinetic energy cannot be constant. Okay, kinetic energy is going to be changed. Okay, it is not constant of time. Okay, so you can see from here this particular thing, that vx square is equal to vy square, it is actually changing with the vy. All right, so vx and vy both are dependent on each other, and these velocities are actually time dependent. Okay, so that's why that is not true. Now we'll go for, okay, so this I can just read the I can just keep this, vx square minus vy square is equal to some constant c, let us say this, let me keep this. Now we'll go for checking v dot a. Okay, v dot a, v dot a is constant of time. See, v, what I can write, I cap vx plus j cap vy dot acceleration side vy by m vy by m I cap vx by m j cap. Now if I take the dot product, so this will be vx vy by m plus vx vx into vy okay. So see this is again, so v dot a on the right hand side also you are getting in terms of vx and vy which are actually changing. Okay, so this is also not correct. Then let us see other option, this one. See, a varies due to magnetic field. Here there is no uh, information about the magnetic field, so better not to much worry about this option. We'll just check with this. Okay, quantity v cross a. So v cross a, v I am taking as vx I cap vy j cap, acceleration vy by m vx by m j cap. Now if I take cross product, so I will be 0, ij will be k, so this will be actually, so vx square by m ij will be k cap along k cap, and v like I j k, so j I will be okay, so minus, so v square by m into k cap. So we get what is 1 over m vx square minus, okay, this will be a vector quantity obviously. So you can see here this particular term we had got already. So I'm sorry, I had actually erased it. So that particular term was vx square minus vy square was equal to c. Okay, I had taken like that. So we can write this as c by m. Okay, c by m. So therefore this is actually a constant. So v cross a is a constant of time. This is correct option. Okay. Okay, so let us go to the next problem. So this problem is again interesting problem. A particle A of mass m1, particle A mass m1, and it has velocity given already. So v1 is root over 3 I cap plus j cap. I'm sorry, this, let us take this as v, because v notation, or u, let us take u, because v1 v2 notations are coming. So a particle of mass m1 moving with velocity root over 3 I cap plus j cap meter per second collides with another particle v of mass m2 which is at rest initially. So there is another mass b, it is at rest initially, and let us say v1 and v2 be the velocities of the particle a and b after collision respectively. So v1 after collision v1, and after collision this is v2. If m1 is equal to 2m2, so m1 is equal to 2m2, this information is given. Let us say this is okay. So m1 is equal to m, so m1 is equal to m means m2 okay, m2 is equal to 2m. So I'm just taking that after collision. After collision v is given here, v1 is given. So v, this is actually v1, this is the velocity of the particle 1 after collision, particle a after collision. Then what is the angle between? The question is very simple, the angle between v1 and v2. So this is a collision problem, not too much difficult. So what you have to do, we have to use conservation of linear momentum. Okay, so we have to apply conservation of linear momentum. Let us do it here and then get what we are getting. So initial velocities are given. Initial velocities for the A is body A is given. B was at rest initially. Okay, so it is very simple if we just apply. Say initial so if I applying conservative so if we apply linear momentum conservation, then see what we get. Initial momentum is equal to final momentum, that's it. So initial momentum is equal to final momentum, linear momentum. And what are those? See, mass of m1 is 2 m2, so that's why I'm taking 2m. sorry, velocity initially was root over 3 I cap plus j cap, and then finally also this guy will have certain velocity. So we have to find out what is V2. So M I can strike out. Okay, or another word, minus okay, so we have got V2 and we have been given V1. I have to find out the angle between them. See, if I try to draw the two vectors over here, say, I'm sorry, I need little bit of cleaning here. Okay, so let me draw it here. So V1 is I cap root over I cap 3. I think root over 3. Yes, root over 3j. So V1 is this. So what is the angle here? Tan theta is equal to y by x, right? So root over 3 by 1. So theta is theta 1. Say theta 1 is nearly 60 degree. Okay, so if I draw here, it's 60 degree. So this is actually V1 is making an angle with horizontal. Now I have this vector. So this, you look here, tan theta will be minus 2 root over 3 minus 1. So this is actually this indicating theta must be minus 45 degree. Okay, minus 45 degree. So if I take all the angles this side positive, so negative will be this way. So this is 45 degree. Okay, so this is 45 degrees. So I have got direction for V1 and V2. Now if I see the angle between them, if this is theta, this is theta, so 2 theta. Okay, so sorry, these are not theta anyway. 2 into 60 plus 2 into 45. Okay, so angle is this one. Okay, 60 degree plus 45 degree. So 105 degree angle between them. This is the answer. Again, so we have got this answer for the question number 3. We'll go to the question 4. This question says linear mass density of a thin rod AB of length L varies as the length of the rod is L. Mass density lambda, that means mass per unit length is varying as this. Okay, so where x is the distance from A, like this. Okay, now if you want to find out, say if the mass m of the rod, then its moment of inertia about an axis passing through A. So this is A, this is B. So that means this is where axis passing through A and perpendicular to the length of the rod. So you know normally what we do, integration dm into x square. Okay, if I consider a small element of thickness dx at a distance x, then I write moment of inertia, elemental moment of inertia dm into x square. Okay, so this is elemental moment of inertia. Whole moment of inertia should be integration of this. And this limit has to be this. But here one thing we don't know, this dm. Dm is mass of that element. Dm is equal to mass per unit length lambda mass per unit length into dx. Now lambda is not a constant lambda. So if we want to calculate the total mass m, okay, so dm is this one. We can go for integration now. So I will be integration di, that is 0 to L, dm is lambda 0 1 plus x by L into dx. Another x square will be multiplied here. Okay, so x square, this is x to the power 4 by L into dx. So if we integrate, then what we get here? Sorry, this is lambda 0 L cube by 3 plus lambda 0 L cube by 5. I just tried one L from both numerator and denominator. That is what I have done here. Okay, so if m be the mass of the rod, so from here we have to, so lambda 0 into L, if I take common, what are the options given here? Let me cross check once again. So this is x by L, this is 1 ml, this is fine, this is also all right. Okay, I think better to just check once what is m. M is actually lambda x into L. So if this is lambda 0 whole into 1 plus x by L, so I'll just integrate it because this is varying. Integrate 0 to L, this is lambda x into dx. Okay, so this is where is the point. So lambda 0 integration 0 to L 1 plus x by L into this. So lambda 0 L plus L by 2. That means, this is 3 by 2 lambda 0 into L. This is actually total M mass. Let me check here what we have got. So lambda, we have to put the value of mass. Okay, we have to put the value of mass m. So lambda 0 L 3 by 2 lambda 0 L, that is the total mass. Lambda 0 L, lambda 0 into L. So let us do this first. L cube 1 over 15, and this is 5 plus 3. This is 8. 8 by 15. Let me check once again. So lambda 0 L, if I write 3 by 2, okay, so I have to multiply 2 by 3 into, this is 8 by 15. So this is my m. 1 L square will be there. Okay, so this is my m. So 16 by 45. 45. I don't think there is option like that. 3 by 7. 7 by 18. 7 by, let me read once again the problem and see where we have done the mistake. The linear mass density of a thin rod AB of length L varies from A to B as lambda x is equal to 1 plus one plus lambda into lambda naught into 1 plus x by L. So this much is fine. Okay, so this distance where x is the distance from A, yes, that is fine. M is the mass of the rod, this is also fine. So we have got the moment of inertia. Let me just cross check here of what we have done. So mass is also fine. We have got 3 by 2 lambda 0 into L. Only this we have to find out. We have to find out I is equal to 0 to L. See lambda x square dx. Okay. So this is what is the thing. Now we have got 0 to L lambda x. We'll put the lambda x lambda x is equal to lambda 0 plus, sorry, 1 plus x by L into dx. Okay, so from here, and 1 x square also will be there. Okay, so x square, so lambda 0, this will be x cube by 3 plus, okay, so there was the problem. So this is x square, x cube, so x to the power 4 by 4. I see, I had written 5, so that's why there was the problem. So 0 to L here. So we can see easily that this will be 12. So 3 and 4, 7. 7 by 12 lambda 0 L cube. Okay. So we know 3 by 2 lambda 0 L. This is actually capital M. So rest you get here. See, you just multiply 2 by 3 instead. and L square is there, and also we have 7 by 12. Okay, so I have just multiplied 3 by 2 here, 2 by 3 here, 7 by 12 into L square. Okay, so this is this, so this is capital M. Okay, this we had already calculated earlier. So this will be M into 7 by 18 L square, or 7 by 18 M L square. Okay, this is the answer. So there are options there. Yeah, so this is the option. Okay, I'll take one more question from this particular sheet. So one more question I'll take for today's session. The question is, in a dilute gas, this is analytical question, not numerical. In a dilute gas at pressure P, and temperature T, the mean time between successive collision of a molecule varies with temperature as options are square root of T, option B as T, option C 1 over root over T, and option D says it is 1 over T, inversely proportional to T. See, collision time, okay, mean collision time tau, that is relaxation time, which is actually lambda, that is the mean free path length. Okay, this is actually mean free path, length of mean free path, length of mean free path divided by mean velocity or RMS velocity you can take. Okay, average velocity or RMS velocity, you take RMS velocity itself. Okay, now we have to see the expressions. Actually, this is a memory based question. So lambda mean free path is actually having an expression square root of 2 pi n. N is the density of the molecule, and this is d square. D square is the diameter square. Okay, and this VRMS and VRMS is actually directly proportional to root T. Okay, this varies as square root of T. Now if we put it here, look, this will be kind of, let us say kt, some constant will be there. RMS actually 3RT by 3RT by m or something like that. I think 3RT by m, root over 3RT by m. Okay, so this is I think VRMS. So anyway, I'm taking other things as constant. So look, this lambda mean free path is this, and VRMS is actually some k square root of t. Okay, that means what? Tau is depending on inversely proportional to the square root of t. Okay, so option C is the correct answer for this question. So we'll stop it here for today. Next day we'll continue with this 6th September 2020 shift 2. The other questions we'll discuss. Thank you for your patience.